Okay, so value iteration is pretty straightforward and pretty effective, as we showed it will converge, but it has several issues. Let's discuss those issues and see how we can resolve those. Okay, so as we saw, value iteration simply repeats the Bellman updates while keeping the previous state estimations as constant and then constantly updating them over iterations. So first of all, the first issue that we saw, that we observed, is that it's fairly slow to compute, right? So per iteration, we need to take, for each state, we need to see all possible next state that we might arrive at, times all of the actions that we might take in order to arrive there. So the computation for a single iteration is a complexity, a time complexity of s squared, where s is the size of the state space, times the action space. And then you might ask yourself, do we really need to update every state at every iteration? As we've seen previously, at the beginning, most of them just state zeros, right? So can we find out which states do we probably need to update and which we can just not update at the current iteration? Next, issue number 2. The policy, even once we converge, the policy cannot be easily extracted, right? At the end of the day, we're not interested in the state values, we are interested at a specific policy, the optimal policy. But in order to extract the policy, we need again to do a full sweep over the entire state space. So extracting a policy is again s squared times a. Might be pretty costly. Issue number 3, the policy often converges long before the values. We actually just saw that, right? Can we identify when the policy converged and the policy doesn't change anymore, right? So we might get more accurate state value estimations, but it won't change the optimal policy that it results in, right? So I don't care about converging of the state values. Let's converge on the policy directly. Issue number 4. Well, as we said initially, this in order to use the value iteration, we must know the model of the MDP and the reward function, right? In order to actually use the Bellman equation. And this is, as we said at the beginning of this lecture, that's usually an unreasonable assumption. Issue number 5, it requires a discrete or finite set of actions. Else we won't be able to iterate over all of the actions. It actually also requires a finite set of states, else we won't be able to iterate over the states. And of course, in real-world applications, in many cases we have continuous action spaces and continuous state spaces. So eventually this will not be a useful algorithm in many real-world applications. Issue number 6, it's infeasible to apply this in very large state spaces, even if they are finite. We can't apply this algorithm in very, very large state spaces. It would just take forever. Okay, so I'll quickly go over the solutions for these issues. These are solutions that we're going to discuss throughout the course. I'll just give you a hint towards where we're going, right? So first of all, in order to solve the issue where value iteration is slow, because we have to go over the entire state and action space per iteration, so we're going to see a simple fix to that is called asynchronous value iteration, where at each iteration we pick a single state and update that one, and that allows significant speed ups in the computation. Issue number 2, the issue with that the policy cannot be easily extracted. So instead of learning state values, we're going to learn Q values, so state and action values. And this will allow us to directly infer the optimal policy, right? If we learn Q values instead of state values, this will solve this issue. We'll also define Q learning instead of state value learning. Next, the issue that the policy often converges long before the values. So we did see a policy-based approach previously, right, in the multi-arm bandit case. And we will also define policy-based methods for MDPs. And we'll see how these allow us to quickly converge on the policy. they have their pros and cons, and we'll discuss that later. But in any case, this will be an approach that allows us to converge on a policy and to identify when we converge on a policy. Issue number 4, we just discussed that it requires, these solutions require us to know the model and the reward function. And I said that we're going to drop this assumption later on, right, with algorithms that actually do reinforcement learning. They don't assume to know everything and then they optimize offline over an MVP, but they assume, we don't assume to know that, and we learn from interaction with the environment. These are reinforcement learning algorithms. We'll see these later. Issue number 5, it requires a discrete or a finite set of actions. In order to avoid that, we'll see policy gradient methods. We'll see that later on. In order to do that, we need to use function approximators and policy approximator, which will also help us generalize our knowledge over very large or even continuous state spaces. We'll see those solutions later on. So in a bit of more detail, specifically regarding issue 1, we'll just try to fix it now because this is a simple fix to the value iteration algorithm. So first of all, value iteration is indeed slow. It has a complexity of s squared times a per iteration, where s is the size of the state space, and a is the size of the action space. So in order to address this issue, we introduce asynchronous value iteration. So in value iteration, we update every state, all of the states in the environment in each iteration. In asynchronous iteration, we update one state per iteration. And actually, this is fine. So any sequence of Bellman updates will converge if every state is visited infinitely often, regardless of the visitation order. So I discussed the term infinitely often previously. It means that at infinity, after an infinite time of updates, in this case, any state in the environment will actually be updated an infinite amount of time. So there is no time point after so many updates that you've done that you at that point you stop updating one of the states. Okay, so at infinity, each one of the states will be updated an infinite number of times. So the idea here is to prioritize states for updates, whose values we expect to change significantly. So we pick the state that will say, okay, if I'll update this state, then I will change the state estimation significantly. So how can we estimate that? So let's start with more of an intuitive way of doing that. So again, I'll ask which state should be prioritized for update in iteration number 1 for our example problem?
The state closest to the terminal state?
Right, we've seen that before, right? At the next iteration, only this state will be updated.
Yes.
So it makes no sense to do a full sweep over all of the states. Probably we only need to update this state here. Here. Okay, so this is indeed what we do in prioritized value iteration. So at each iteration, we choose a single state, the state with some maximal heuristic value, which tries to approximate the update that we're going to perform to this state. And we do a Bellman update only for this state, only for that state. And then for all of the states that might be affected by this new value, we recompute the priority for them. Okay? And we continue this process. Again, this is value iteration, but we only update one state per iteration. And in this case, we have the SDS function. These are just all of the states that might be affected after updating state S prime. Okay, specific state. For the home assignment, in your home assignment, you are required to implement both value iteration and asynchronous value iteration. For your home assignment, please use the following priority function, h of s, which is simply the expected change in the state value after you do a Bellman update. So you actually compute the Bellman value, this new value, and you observe that value with respect to the current value that is assigned to each one of the state, and you say, well, if I would update this state, but how much would it change? Now this might sound a bit weird, why? Right? Why? Because I'm doing double the work.
Yes.
So I'm telling you, do the Bellman computation, don't update the state, use that Bellman computation in order to assess by how much you're going to update the state. If it's the maximal, if this state will be maximally updated, then only update it. This seems a bit strange, or might seem, it seems like double the work. Because computing priority according to this rule is similar to updating the state value, right? The same computational effort. Why do double the work? Well, in different words, if we compute the priority, we can just go ahead and update the value for free, right? But this is not exactly the case. We don't have to sweep over the entire state space in order to always keep track of that age of S value, right? Please notice that we don't need to update the priorities, this age of S value, for the entire state space. For many of the states, the priority doesn't change following the update value of a single state S. So we only update the priority for those states that might be affected by the state that was updated in the previous iteration. If we wouldn't do that, if we actually compute the priority and then also do the update, then all of the priorities would have changed. Okay, and if you don't have to take my word for this. Actually, you will implement this algorithm, both value iteration and asynchronous value iteration, with this priority function, and you'll be actually able to see that it's much faster in many cases, in most cases. Okay. Next. So a second issue that we would like to address, a second issue regarding value iteration, is that a policy cannot easily be extracted once we converge on the state values, or given any state values. It's not straightforward to infer the optimal policy. In order to extract the optimal policy, we would need to perform another full sweep over the entire state space. But instead of computing the state value, as we do normally with the Bellman equation, we now compute the action that maximizes the state value. So now we will have to compute the argmax over each one of the states. And again, this requires another full value sweep at the complexity of S squared times A, where S is the size of the state space and A is the size of the action space. So one way to address this issue, that is to avoid the need to compute the optimal policy, would be to learn Q values instead of state values. Okay, so just as a reminder, the Q value, specifically we would like, of course, to learn Q star values, that is the Q values for the optimal policy. So just as a reminder, the Q value or Q star value for any state and action pair is the expected sum of rewards from being at state S, taking an action A, and then following the optimal policy pi star. So once we converge, once we learn the optimal Q value, the Q star values, then the optimal policy is straightforward. We simply take the action at every state, we follow the action that maximizes the Q value, with the highest Q value. Right, but that's it doesn't require us to perform a full sweep, and we can do it per state. And now the question is, can we adapt the value iteration algorithm to learn Q values instead of state values? That is, can we use dynamic programming, as we did before, to learn Q values? And the answer is yes, and we do it in a very similar way to value iteration. So let's look at the definitions of Q values and state values and see if we can easily adapt value iteration to work with Q values. So I have here the definition of the state value, right? Specifically the state value under the optimal policy, V star. Okay, it's just the value of the action that maximizes this term, right? The expected sum of future reward. So it's the probability of arriving at each one of the next state following a specific action times the immediate reward that we're going to observe after following that action and arriving at the specific next state, plus the discounted sum of reward from being at the next state onward. Another definition of the state value is simply the maximal Q value over all actions at the specific state, right? So we're saying that V star is the policy that follows the best action, right? The best action in a given state. And so now we can have a look at our definition of a Q value or the Q star value. This is simply, now it's very similar to the definition of V star value, but now we do it for a specific action, right? Given to us in the Q function. So now we don't have to maximize or iterate over all possible actions, but for the specific action, we compute the expected sum of immediate reward plus discounted future reward. But given these definitions, now we can easily substitute the state value term here in the definition of the Q star value with the max A Q star value as defined here. Okay, so we can simply substitute that, and now we have a Q star value, definition of a Q star value that only depends on other Q star values. Right, this is what we saw previously with the value iteration. And so once we define this, we can easily run an algorithm, actually the exact same algorithm as before, the value iteration algorithm, only now converging on the Q values instead of the state value. And as before, we solve these values iteratively. So we set a Q value at the current iteration, and so this is the current iteration, right? Iteration K, or the previous iteration. So we use the Q values in the previous iteration in order to compute the Q values in the next iteration. Okay, and as with value iteration, we can also do asynchronous learning. That is, we don't need to perform a full sweep over all state and action pairs in the state and action space. We can actually do it in any order. We can update state and action values in any order, and that as long as we do it infinitely often for each state and action pair, we are still guaranteed to converge. Actually, this is performed in many state-of-the-art reinforcement learning algorithms. That is, while assuming that an agent actually interacts with the environment and observes state and actions, the agent will follow a very specific sequence of state and action pairs and will do Q updates for those state and action pairs. And again, as long as we guarantee sufficient exploration, that the agent travels or explores the entire state space and action space, these algorithms are guaranteed to converge. Question?
Yes. Does Q-learning have the same time complexity as value iteration?
Per iteration or until convergence. So convergence is domain dependent, right? It depends on the reward function, on your learning rate, and stuff like that. If you're doing full vanilla or full value iterations over the entire state and action space, then yes, I would say in order to do a full sweep, you'll need to go over the entire state and action space